So today we're going to focus on kind of two really key and fundamental factors in hydrogeology. And the first one is determining what is called total head. And total head is a sum of pressure head and elevation head. And we're going to want to be able to convert between units of depth and units of pressure and be able to quantify the kind of hydraulic gradients. And then we're also going to identify the direction of groundwater flow. So that's kind of our general key goal for today. So groundwater flow is governed by pressure and elevation gradients. So again, the sum of the two create what is called total head. And the hydraulic properties of the geologic units then impact the potential or rate of flow in these environments. So you have the pressure and the elevation gradients creating the total head or the potential for work. And then these are further influenced by the hydraulic properties or the connectivity of pore space in the subsurface in the aquifers. So this is just to give you an idea of kind of what maybe a hydrologic setting would be. And we're going to go into some of these vocabulary like unconfined and confined aquifers later on in the course. But the whole goal demonstrating here is that oftentimes as a hydrogeologist, what we're trying to do is we're trying to understand if we were a drop of water here, what is our likely direction to go, right? Are we going to be moving downward? Are we going to be moving left or right? Those are the kinds of things that we're trying to determine. And inevitably, when we begin to determine that, we can begin to determine, for example, well, how much water would we need to recharge an area if we're pumping at this volume? Well, we know the flow rate that's going to here. And so we can determine whether or not this kind of thing like pumping over here would be sustainable in an environment. And, or for example, if you're thinking about maybe salmon populations in a stream, we begin to understand what time period of water and what flow directions of water are coming into here, and whether or not maybe a change in climatic conditions like inputs of precipitation over long periods of time may make this stream more vulnerable or less vulnerable, depending on these flow paths that we're looking at. So that's kind of our goal today, is to begin to understand what governs flow. So here is a schematic, and this schematic here has our overlying, generally speaking, our bedrock. So let's take a look and see. I'll draw our bedrock kind of in brown. So here's our bedrock. There's some sediment above this bedrock, but this is kind of what we consider low permeability bedrock. We have it filled with this sediment here, and then we have identified on here where the water table is. So we've gone out and we've measured and we've said, okay, this is where the water table is. So below this is all saturated, right? It's filled with water. Now, our goal as a hydrogeologist would be to say, okay, if we were a water drop here at point A, what would our flow path likely be and where would we end up? So we can think about what is actually making water flow. And from measurements taken, and we'll show you later on, that water is going to be flowing kind of from A to C, right? That's kind of our general direction. But if we think about what makes water flow, if it was only just gravity, and let's think about that, which way would water flow? So if we look at the flow paths, gravity could explain water flow from A to B, right? That would make sense. But how would gravity explain water flow from B to C, right? That would be almost against gravity. It wouldn't quite make that much sense. So pressure, right? The pressure at point A is equal to the atmosphere. The pressure at point B is going to be greater than the atmosphere, right? It's not up at the top, but it's further down, right? So we have something pushing on it more than just sitting at the atmosphere. And the pressure at sea again is the atmosphere. So what is making this water flow? So when we start to think about the water flow itself, we can begin to think of what's a term called hydraulic head. So hydraulic head is, or total head, is oftentimes underscored by something that is like this H that we see here. And if we were to drill a well into the ground, let's say this is our well over here, and we have some datum. Now this datum could be any kind of datum. It could be sea level. It could be any of the global geodetic datums that we may have so that we can put them on similar scales. When we think about this datum, when we measure from this datum here, and we could again say that sea level, to where the groundwater rises up into this well and could be measured here, that total depth or length is H, and that's our total head. Now it is, that total head is the proportional energy that is allowing for the fluid of water to move. And it is broken down into two key components. It is broken down into what is called the elevational head here, Z, and the pressure head here. So when we take a look at this, right, our total head, right, which is the water level above our datum, is a component of our pressure head and our elevational head. Now we're going to just take a moment. I'm going to let you write this down in your equation sheets because this is actually a very, very important equation for all of the rest of our class, understanding how hydraulic head is calculated. Now, one component of this, right, is actually understanding what pressure head actually means. And so pressure head here is going to be the pressure that could be felt, and right, we would be measuring that pressure down here, right, at this point, located here, divided by the density of water and gravity. So these two values are the same thing, but this lets you know how we actually physically measure it. So oftentimes what we do is we put a sensor down in here and we measure the physical pressure. It pushes on, the water pushes on a diaphragm in that sensor unit and allows us to understand the pressure, which we can then calculate into a depth using an equation like this. So one key component when we begin to think about head or total head, this H, is that water is always going to flow from high head to low head. All right. And that's a very key and important factor for us to always keep in our back pockets, because we may look at a figure and it may intuitively, we may think things may be moving in a downward direction, but we actually need to calculate the head, have to make these calculations at different well points to actually be able to necessarily determine if it is going necessarily the high head and the low head. It's also really important for us to think about the fact that the subsurface is in 3 dimensions. So we may want to calculate the head in the X direction. We may want to calculate the head in the Y direction. And we may want to calculate the head in the Z direction. So we might want to understand how is it moving, for example, toward a stream, adjacent to a stream, and even down beneath the stream, to kind of give you an idea of what these multi-dimensions might look like. So let's kind of go back at least and think about this in more of a 2-dimensional problem, what we were drawing before, just to kind of get it into our head. So here's that same area that we were looking at before. And what we can do is see that we can have water that's moving from a high head to a low head. And so here, when we start at point A, we have a small pressure head, but a very large elevation head. So I'm going to draw that elevation head in brown. So here's our elevation head. So this whole thing down to here is our elevation head. And our total head, right? If we were to think about it right now, we would could kind of draw a line over here. The total head that we have, so that's our pressure head here, plus our elevation head here, is 70 meters from our datum. If we were to go over here to this area B here, again, we have our elevation head to here, right? Then we have our pressure head to here, that's our pressure head. But when we move that over to look kind of at the scale, we might be at about, I don't know, let's say 41 meters. And then we could say, okay, well, what about at C? If we get close to C, well, this well is pretty close to C too, and we can get an idea, right? Here's our elevation head down to the datum. Here's our pressure head up to here. And we'll continue to draw this one over again so we can get an idea. And maybe here we're at about 39 meters. So we are moving, as we move from point A to point C, we declined from 50 meters essentially of total head down to about 39 meters. So always moving from the high head to the low head in this situation. But you see that flow path as kind of follows along here. All right.